Welcome to part 3 of the 4-part video series on applications of quadratic equations. This is going to be all about money. In this type of question, we're going to be considering pricing something appropriately so that we maximize our revenue. So through some market research, we've kind of noticed a pattern where if I increase the price by a certain amount, I'm going to lose a bit of sales. If I decrease my price a certain amount, I'm going to gain a certain amount of sales. And by doing this research, we can find that sweet spot so we maximize our revenue. Because think about it this way, if you price it too low and make all these sales, well, you may have been able to charge more to maximize your revenue. And perhaps if you charge too much for your product, you're not going to sell enough to maximize your revenue. So in this case, we have a sticker warehouse selling rolls of stickers for $4 each. The average customer buys 6 rolls of stickers. The owner finds that for every $0.25, so 25 cents decrease in price, the average customer buys an additional roll. With how many price reductions will the revenue per customer be $30? All right. So what we're going to do is think about, well, what is revenue? So let me just do a little note here, what revenue is. Revenue is the income gained by selling something. By selling a product. And this is going to be given by this equation right here. So revenue R is going to equal, basically your income is going to be the amount of money you earn. And that's going to be dependent on how many things you sell and for what price you sell it for, right? Price per item. So let's let R be the revenue. Let X be the number of items sold. And we'll let P, little p, be the price per item. And I'm going to create one more variable in a moment, but we'll leave that for now. So we need to look at what this question is telling us here. So my revenue is going to be determined by how many things I'm selling. And it looks like, how many do we sell originally? So an average customer buys 6. So let's just highlight that. The average customer buys 6 rolls of stickers. All right, so that is going to be my original number of items I sell. And then my original price per item is $4 each. So there's that and that. So let me just highlight these on here. So we got the 4 and we've got the 6 here. Okay. Next, we need to think about, okay, if we decrease our price by 0.25, so that's going to be a change in our price. So we're decreasing $0.25 from our price. What do we find? The average customer buys an additional roll. So additional. So that's one more roll. So we are going to add one roll to that. And what I want to do is set one more variable. All right. I want to set one more variable in a moment here after I color all these for you. This next variable is going to be the number of decreases in price. So we're not going to just decrease the price by 0.25 once. It's for every 0.25. So we might do it once or twice or 3 times, depending on what is going to give us the revenue that we want. So we can put here and here, right? If I decrease by 0.25 a certain number of times, it's going to buy, the customer's going to buy one more roll. Okay. So we're trying to look here in this question, how many price reductions are going to give us a revenue of $30? So this question's basically saying we're given the revenue here is $30. So in this situation, we could just put the revenue in as 30. After we're done with this particular situation, I'm going to show you a more general situation because I was talking about earlier, like, well, the idea is to maximize the revenue, right? So let's see if this n that we find, this number decreased in the price, is 30 going to be the actual maximum revenue? And we'll check that. Anyways, okay, so let's just go ahead and go about our business here. So to solve this, we're going to need to solve for n, which means we're going to need to expand out these brackets. So let's do that. So 6 times 4. 6 times 4 is 24. And then we go 6 times 0.25. All right, so we got 6, oops, plus, no, it's going to be 6 times negative 0.25. So it's actually going to be a negative number. So we got 6 times 0.25n. And then we've got 1n times 4, which is 4n. And then we have 1n times the negative 0.25n. So 1n times negative 0.25n is going to give you our 0.25n squared. All right, let's clean this up. We want to bring everything to one side. I'm going to actually bring everything over to the left side. All these things are coming over here. And the reason why I chose that is because I just like to have this, the coefficient in front of the n squared term as a positive. It's not required, but it's just something I like to do. So you could still solve it the other way. All right, by bringing everything over, that negative 0.25n squared on this side turns into 0.25n squared, so the positive. And then let's look at what is 6 times 0.25. Well, what's 0.25? 0.25 is actually 1/4, which means we have 6 times 1/4 is 6/4. And 6/4 reduced is going to be, divide top and bottom by 2. We end up getting 3/2. So 3/2 is 1.5. You could just toss in your calculator, but fractions. So we have 1.5n. 1.5n. So let me just replace this. I'm just going to do a little side here. Like say, so we have negative 1.5n here plus 4n. Well, what's that equal to? Negative 1.5n plus 4n is 2.5n. So we have a positive 2.5n on the right side. I'm going to bring it over to the left side. So I end up getting negative 2.5n on the left. And then I'm going to lastly bring this this 24 over to the other side. So now I'll end up having 30 minus 24, which gives me 6. So after some careful algebra, you're going to end up here, however you do it. Now I have this quadratic expression here equal to 0. You could try and factor it, but in this situation, doesn't look like very nice numbers. So I'm just going to use the quadratic formula, which always works when you get your quadratic expression equal to 0. So I'm just going to identify my a value, which is the number in front of the n squared, 0.25. My b value is the number in front of the n. So b is negative 2.5. And finally, the number by itself is the c value, which is 6 here. Using the quadratic formula, I'm going to get what n is. So recall your quadratic formula as negative b plus or minus the square root of b squared minus 4ac and over 2a. So I'm just going to replace all of these values with the appropriate numbers. So b is negative 2.5. And let me just erase this so I can write this properly. So we got negative 2.5 squared minus 4 times 0.25 times the 6. And the a value, once again, is 0.25. So at the bottom here we have 0.25. Carefully putting this into your calculator. Let's see what the discriminant is. So we have n equals negative and a negative gives you a positive 2.5 plus or minus. Okay, what's in our square root? So negative, well, you could just do 2.5 squared. The negatives will just cancel out anyways. So 2.5 squared minus, now we have to be careful with the signs. It's just, they're all positives anyways. 4 times 0.25 times 6. Our discriminant is actually 1/4. So I'm going to write that as 0.25. So we have 0.25 as our discriminant, and 2 times 0.25. That's like saying 2 times 1/4, which is going to give you 1/2. So we end up getting 0.5. All right. Now let's get what n is. The square root of 0.25 is actually 1/2. And think about it this way. If you take the square root of 0.25, that's like taking the square root of 1/4, which is like saying the square root of 1 over the square root of 4, which is giving you 1/2. So it makes sense that we're going to get a value of 2.5 plus or minus 0.5 all over 0.5. One more thing you can do here is, look, you can just put this in your calculator and do it however you want, but if you think of these things as fractions, you've got 1 over 2 in the bottom here. That's what 0.5 is. And using your fraction rules, what happens when you're dividing by a fraction like this, the denominator ends up multiplying the top. It's like you have 2 times 2.5, 2 times 0.5. So what I'm going to do now is just double my numerator. And you'll see I end up getting n equals 2.5 times 2 gives you 5 plus or minus 2 times 0.5 is going to give you back 1. So we actually have 5 plus or minus 1, which means there's going to be 2 possible results. We have n equals 5 minus 1, which gives us 4, or we have n equals 5 plus 6, or sorry, 5 plus 1 is 6, and there it is. In this, so what this is saying to you is, to get a revenue of $30, we can do either 4 decreases in price or 6 decreases in price. So let me just write a conclusion here. Therefore, to achieve a revenue of $30, there can be 4 or 6 decreases in price per item. Price per, we're talking about price per sticker roll. Now, I have a suspicion that this is not going to be the maximum revenue that we could have otherwise achieved. And I kind of get that because we have 2 different answers in our results. And let me kind of explain this a little more. Here is the quadratic expression that we get here, right? But this, let me just do something. Let's figure out, given our general expression, let's not set our equation to be 30. Let's set it to let's just graph this. Let's just graph our revenue with respect to n. So our revenue, R, is going to be graphed like so, n. And let's take a look here. We got 6 plus 1n. What I'm going to do, I'm going to try and copy this if I can. Let's try and copy this down here. I'm going to copy and paste this guy down here. Hopefully it works. Oh, it worked all right. Here's our quadratic that we have. I'm just going to write it without all these colors. All right, here we are. This is a quadratic that I would like to draw. Now, this is conveniently in factored form for us. That allows me to find the n intercepts, otherwise known as your x-intercepts. We're going to find the n-intercepts. So what I can do is let r equals 0 this time. That's going to give me the n-intercepts. And you'll see why I'm doing this. Just to help me sketch this graph for you so you can visualize it. So we have 6 plus n, 4 minus 0.25n equals 0. This gives us a solution of 6 plus n equals 0, or 4 minus 0.25n equals 0, which means we have n equals -6, or n is going to equal, so we have 0.25. Let me just do this in 2 steps just for completion. Let me bring the 4 over to the other side, doesn't really matter. So we got -4 over here. And I'm now going to bring the 0.25 to the other side. So I'm going to divide both sides by 0.25. And that's like dividing by 1/4. You end up getting 16 here. So this tells me, if I go back up here, and let me just quickly do something here. I'm going to extend this a little bit. Just a quick sketch, excuse my shaky lines here. So I'm trying just to kind of show that this graph kind of looks like this. 1, 2, 3, 4, 5, 6. So here is my one intercept at -6. And then my other one's at 16 going the other way. Let me just do that quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, something like that. As you can see, if I did expand this out, you would get, if you look here, you're going to end up multiplying negative 0.25 times n, and that's going to give you your negative 0.25 n squared, which tells me this graph is going to be concave down, right? And hey, why not? Let me just show you this just to be complete here. Let's just erase this stuff here. Let's actually expand this out because we will gain some information by doing that. I'm just gonna kind of go r equals 6 times 4 is 24, right? That's what I did here. 6 times 4. Then I can go 6 times 0.25, which we did before is actually 1.5. So it's going to be negative 1.5. Negative 1.5n, and then we have plus 4n, right? Because we go n times 4, and then we're going to go n times negative 0.25. So we have negative 0.25 n squared. So that's where you see that our quadratic's going to be concave down like this, because this is a negative in front of the n squared term. All right, we have r equals, let's order it properly and do 4 minus 1.5 gives me 2.5 n, and then we have our plus 24. Now, I kind of just did this so I can get this 24, because when we have it in standard form, which is you're looking at here, this last term here tells me where the y-intercept is. And it kind of just helps me get an idea of the graph. Just so I'm just going to just do it like this. It's not going to be perfectly to scale, but there it is. There's that point. Now, my objective here and why I've kept going here is I want to try and figure out what the maximum revenue is going to be based on how many decreases in price I should go. And what I'm trying to do here, let me just kind of sketch. I'm trying to figure out where this quadratic gets to its maximum. And the way we can do that based on these two numbers is to figure out what the average of these x-intercepts, or let me call them n-intercepts, are, right? That takes me, if I take the average of this value and this value, it's going to take me to the middle, and due to symmetry of a quadratic, that middle point is going to tell me the n value of the vertex, which is what I'm trying to do. The vertex is where the maximum is. So let's get to it here. Let's go over here a little bit. So we have n of the vertex is going to be my first n-intercept plus my second divided by 2, and we get negative 6 plus 16 over 2, which gives you 5, because negative 6 plus 16 is 10, divided by 2 is 5. That's the value. This is actually the number of decreases we should go to get the maximum revenue. So the maximum is going to happen here. 1, 2, 3, 4, 5. It's going to happen if I'm just going to draw my 1, 2, 3. I'm going to draw it here. This is where it's going to happen. That's where it's going to peak, and that looks about where I was sketching to hit the maximum value. So let me just keep going. Oops, let's draw it a little better. It's a little ugly. So something like that. All right, so there's my quadratic, and we are trying to find the vertex. Right now, by taking the average of our n-intercepts, we've got the n value. To determine the maximum revenue, we can substitute 5 into this expression or this expression. It doesn't really matter. I'm going to choose the original one, because to me that might be a little bit easier. So let's sub nv, so the n of my vertex, into this equation right here. So that results in a revenue of 6 plus 5, 4 minus 0.25 times 5. All right, so 6 plus 5 is 11. And then 4 minus 0.25 times 5 is 11 over 4, or we can say 2.75. So my revenue is going to be 11 times the 2.75, which is $30.25. So the value that this question asks you to determine is not actually the maximum revenue. It's just a revenue that we chose. Like, let's see if how many decreases to get this particular revenue. But what I've just determined is the R value is $30.25. That is going to be the max revenue I could achieve based on this research data and understanding like how many more sales we'll get per decrease in price. So let me just say, therefore, the maximum revenue is $30.25. If we decrease the price from $4 five times, right? Now, that's kind of an awkward thing to say. How about we say, let's figure out what the actual price is going to be. Why don't we say, so our decreases were 0.25, right? So like we already did this. Like this is the price, right? So the actual price that we're doing when we decrease it 5 times is going to be 2.75. So when we decrease the price to $2.75 per roll. There you have it. There's a very common money example. This is something you'll see in quite a bit, not only in the grade you're probably in, but it just keeps coming back around. So learning kind of these details that I just kind of outlined for you will really help. Coming up with this expression at the beginning, this one right here, is the key. So go back and listen again to my reasoning of how I came up with this right here, because this is the tough part, right? And then understanding kind of what your variables are representing and what you're really doing here. All right, well, I hope this helped. Feel free to continue on to part 4, which is a few physics examples. Hope this helped.